Okay, it's time to start. Not so many people here, as Isaac has told. Maybe people is preparing for the match. Still some hours to go, but in any case, we should start now. Let me present myself and my colleagues. I'm Alberto Fernandez from the Dusty Institute at University of Granada. We will share this tutorial with my friends and colleagues, Isaac Triguero from the School of Computer Science in the University of Nottingham, and Miquel Galar from the Institute of Smart Cities and the Public University of Navarra in Spain. And this is the tutorial, the hands-on tutorial on Apache Spark for solving data science problems with fuzzy logic. You have the link to the slides in the chat, but also you can use this QR code or the URL link I just put in this first screen. Okay, so what are the topics we are going to talk about in this tutorial? Well, many things, because this is big data, and therefore we are going to talk about big things. Big data for sure, but also data science, which is closely related to this topic. And for sure, it's in the title. Apache Spark is the framework, the current framework that is widely used to address this kind of problems. Also Hadoop, which is the infrastructure. We are going to talk about technologies, complexity, different approaches, interpretability related to fuzzy logic and fuzzy systems, for sure. So this is all the things that will be covered in this session. And this is the outline of the presentation. First of all, an introduction to big data. What is big data? Why big data? How do we deal with big data? Then we will come along for one very interesting issue, that is how do we adapt or redesign machine learning solutions in general, and fuzzy-based models, fuzzy rule-based models in particular for big data and data science. And after all these issues will be introduced, and we have more or less the basis and some knowledge about the topics, we will proceed with the hands-on tutorial, and we will provide you with a couple of links in Google Colab. I don't know if you are familiar with this tool, but you can follow us live in a shared notebook, and this is very, very interesting to learn by doing. And finally, we will make a short discussion and concluding remarks about challenges and future prospects in the topic. So let's start on what is big data. Because yes, big data and data science, this is well known for years, but maybe some of the attendees are not so well known to the topic. I have worked in machine learning in general, but what is this big data and what is so popular? What are the features of big data? And to start with, I want to share this quote from Dan Ariely, because he said years ago, but for me this quote is also recent, because big data is like teenage sex. Everyone talks about it. Nobody really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they are doing it. So most of the corporations, people in academia, more or less, I'm putting in the paper this buzzword, big data here, big data there, because it's a trend. But nobody really knows what big data is, or at least what are the specific issues that define big data, and what is big data and what is not big data. And about it grows so fast in the later years that you can mostly see, maybe not, but here you can see more or less that it grows large and larger every year for data science notebook platforms, computer vision, and we have here plenty of things regarding open source here, which is what we are interested in. So frameworks, data flow, data access, databases. So there are plenty of solutions already in big data, but we need to know how these solutions work. What do we need the skills that we need to use all these tools and frameworks, okay? So this is what the tutorial is about. And big data is so important because it allows us as a society, as researchers, to make big improvements, for sure. And the center of everything, the core, is the value that we obtain from the data. We capture information, and we capture information in mostly very, very specific areas of study. We think about social media for profiling and advertising, among others. We are having lots of information because the human body is a data generator, and we think about accurate diagnosis and personalized medicine. We are thinking about smart cities with the Internet of Things, Internet of Everything, and we are thinking about Industry 4.0, the next generation of industry, the fourth industrial revolution. And this is the importance of big data, how we can take all this huge amount of information and transform it into valuable knowledge. And the current definition of big data involves not only volume, because we are thinking about volume, but there are all other V's that altogether define what is big data. And we must think about variety. You have shown previously that data can arrive from different sources, and we have heterogeneous data. And we have also data flow. We have data streams arriving to a system and need to be processed in real time. And because we are getting so much information, information can be corrupt, can be dirty information. We need to transform this big data into smart data. We need to be sure what information we are acquiring, the information is that the data quality of this information, to be able to extract knowledge from it. And this is the 4 pillars of big data, the 4 V's that defines big data. But because there is no standard definition, here's a definition that we think that is quite interesting, that big data involves data whose volume, variety, and velocity that makes data to be complex. And the issue here is that this kind of data requires new techniques, algorithms, and analysis to extract the knowledge. Why? Because with the standard tools and techniques, we are able to run it into a single machine and run scikit-learn and run R and run our common tools and frameworks. But the standard algorithms cannot cope with so much information. There is a threshold. And when this threshold is reached, we need to go on to data-intensive computing. And big data is related to data-intensive computing. We do not need a single machine anymore. We need to go to high-performance computing. We need to go to parallel computation, and we need to change the way we design and use the machine learning algorithms. Okay, and this is very important. This is what we are going to show you here, that now we need to go to other tools. We need to think other ways to develop our algorithms. And there are also other things that are related to big data. We know that for the data collection, we need to do some web scraping or APIs to extract the information. To store the data, this is also one issue that we need to answer. How do we store the data? In the standard relational databases, sometimes it's possible, but mostly because data is unstructured, you need to use a different system. How to extract knowledge with machine learning, but not the standard machine learning. And the most important issue, we need to summarize everything into a single visualization to compress the information, compress the knowledge that we have obtained. And this is done with different new techniques and tools. You can see here Flume Kafka for data fetch, Hadoop and MongoDB for the storage, special packages for R, Python, and for sure Spark, which is the core of this tutorial, and for sure to put into value visualization in business intelligence like Tableau or D3. And this reminds us very much of the data science life cycle, which is quite known nowadays as the ML ops. Okay, so this is a smooth transition from one to the other side. And finally, to get the motivation here, what is big data and what is not big data? Big data, for example, is used in large-scale statistics, so non-standard statistics. When we think about finding shopper correlations, A/B testing for clickbaits, where there is many information involved. Data clustering for client segmentation strategies, analyzing campaign targets, okay, or robust predictive models in very specific problems like fraud detection. Imagine the large amount of files that a company may have, customer churn, or even to determine stock prices. So this is what big data is made for, okay? Now I leave you with my colleague Isaac, which will tell you about why big data and how to deal with it.
All right, very good afternoon, everyone. Can you please unshare your screen, Alberto, so I can share mine?
For sure. Mind.
Thank you.
I thought it was possible.
It's not the straight way until you unshare here.
Can you?
Yes, so now you should be able to see my screen.
Perfect.
All right, fantastic. Thank you very much, Alberto, for that. So as Alberto was saying, what is big data? And I hope that by now you're very happy and content on what big data is. So what I want to speak now about is why we need to bother with big data. Why exactly is what we need to do different to deal with big data? That's kind of the point that I want to discuss in this second section of the introduction. So we need to change a paradigm. Why? Because we are dealing with massive amounts of data, and we will have problems when we try to use that kind of data in our computer. So if you think about, for example, you're running your favorite machine learning algorithm, let's say your decision tree on your laptop, right? And at some point you say, oh, damn it, I'm trying to run this bigger data set and it doesn't really quite fit in my main memory. So you get a memory error, or the data set that you're handling, it doesn't really fit well on your hard drive or a solid state drive. So therefore, what you think of is what we call scale up, right? Vertical scalability, which is, okay, I need to run this. I don't have enough memory. I'm going to try to upgrade my laptop to get, or my desktop computer, just to make sure that it is capable of dealing with the amount of data that I have to deal with at the minute. And whenever that is possible, I would say, please go for that option. Whenever you can actually run it in one single computer, it will be better. But whenever we talk about big data, we are talking about what is here underneath. We're talking about scale out. We are talking about horizontal scalability, in which what we are trying to do and what we are aiming for is to spread the cost, the processing of information across a number of computers for them to be able to solve tasks more easily. But that actually, however, becomes slightly more difficult to design. So in summary, scale up is all about, you have your own desktop computer, your own laptop, and whenever possible, you try to do everything there because it will consume less energy. It will not need any special cooling systems. It's going to be nice and easy. You can use any library you want from machine learning. The price will be a problem if you need to start upgrading it much more. But we say there here in the slide is not fault tolerant. And I'm going to get back to this in a second. What is a scale out? Scale out is just simply the idea of putting more computers there available for you. And why is that good? Well, having more desktop computers, more computers, more nodes will make it easier and it's cheaper because you don't really need high-end computers. The problem with that is that having more computers, it will, in the end, cause other issues. Like we need to think a lot about how we're going to design the software to be able to run and process information across. And we will have problems with the network, right? Because we will have to move things across the network as well. However, the good thing about that is it is fault tolerant. What does it mean? Imagine that you're running something that takes 24 hours to run. If you end up having a problem in a single machine and that one breaks down, what is going to happen is that you need to restart your processing from the beginning. If you scale out, if you use multiple computers, they are taking partial tasks. So therefore, they don't have a problem to restart one particular half or a quarter of the data or 20% of the data that that particular node that broke down is managing. So some other node will take over and do that for you. So fault tolerant and mechanisms will be possible in here. So in summary, what I want to say here is whenever we think of big data, we're thinking about something that needs more than one computer. So probably you're now thinking, Isaac, what you're talking about is simply HPC, right? So you're talking about a number of computers that are all connected across via a communication network, InfiniBand if you're lucky, and then you will have central storage, and all of that will be connected through a network input-output, right? So each one of these nodes will have an operating system. Hopefully it will be Linux, and therefore everything will go well. And what we used to do in HPC was you have a relatively small amount of data and you spread that across all the nodes. And then what is going to happen is we're going to have loads of communication and moving things around, but that is just the communication moving through the network. However, when you have to deal with big data, that will not quite work. Why? Because what you're going to have is this network that was sharing all the information, all the data for all the machines will be collapsing this network. Rather than using the hard drives that are locally here available, we're not using it. We're using the central storage, and that's going to be a problem. So the solution for big data is not to use a standard HPC approach. Is to use something else. Is to use the local drives that you've got in your in every single server and every single node of your cluster. And in here, you're going to have partial information. So you're not going to have the entire data set in one single node because it will probably not fit in that particular node. But what you have is some replications here. So you will see B, for example, here and also repeated here. And if you're wondering why is that, it's just in case this one here actually fails. So then you can actually still take over and process that part of the information. So this is the main thing we're going to try to do, is to reduce moving data across the network. We want to do everything locally. And that's what we mean by the principle of data locality. We're going to try in big data always to apply the operation in such a way that we don't move data across the network, because the network will be very, very slow. So bottom line is, in a nutshell, what we want to do in big data is distributing computing. We want to apply an operation in all the data that we've got. We cannot do that in one single machine. We need to use multiple computers. You don't care about which machine is running what. You don't care if one machine breaks down. What you care about is that you get the job done. And you want that to be completely transparent to you. You don't want to know all the complexity of things moving across the network. You just simply want to say, this is my data set, it's bigger than my machine, please use more machines to do this. And for that, data locality and try to avoid data transfer across machines, that will be super important. So that new shift in the way we think with high performance computing is all about moving computation. Is going to be cheaper than moving computation and data at the same time, right? So what we're going to do is to try to keep the data as much as possible in local drives of our nodes in the server, and what we send around is his function and operations that need to be computed there, right? So that's what we're going to try to do, and that was the main principle behind MapReduce. And I guess many of you, and it would be nice to know if you can type it in the chat, who knows what MapReduce is, right? So I'm going to try to explain it, but I'm going to go really, really briefly, because then in the actual hands-on session of this tutorial, Mikkel will be talking about this. So formally speaking, MapReduce is a programming paradigm that is based on functional programming, in which the user will have to specify and define two different functions, a map function and a reduce function. Basically, you can see this as a divide and a conquer. You split the data, you do something with the data, you shape it, you do whatever you think it might be good to do with that partial data to later on reduce, aggregate, and get something out of it, right? So the way it works is slightly more complicated than just the way I explain it. It works on and operates on these key value pairs, and things become slightly complicated, but I hope with the example that Mikkel will show you later on, you will be happy with it. And I'm going to just give you a bit of a hint on how these things actually work on the Hello World example of MapReduce. The Hello World example consists of counting words in a really huge document. So imagine you have a very, very big text file with loads of stuff there, and we just simply want to count how many times the word welcome is repeated, how many times the big word is repeated, and so forth. So here in this figure, for example, what you are imagining here is a big file of one line, a big file of one line here, and another big file of one line. This is in one node, this is in a different node, and this one is in a different node. The map function, what it could do is to simply say, well, my input is like this. I'm going to be working on this key value pairs, but the key of the map phase, the input map phase, is quite irrelevant most of the times. And what you want to say, what this could be doing is to simply say, hey, I've seen the word welcome one time, and this is the output from this processing this one, the word to, the, or world, you've seen it once. So that's what you can do in the map function, right? So then what happens is, well, you might be wondering what is this in here, right? So there's a bit of a repetition, and if we were to have the time to discuss combiners, that could be actually be handled within this node before it goes to the next phase. So the next phase is something that happens automatically. Things will be sorted according to the key that you are outputting from the previous phase. So if you remember from the map phase, what I did is key is welcome, and I said the value is going to be 1, meaning I've seen it once. I've seen it once. Now what we do is automatically things will be moving actually across the network, so you need to be careful with that. And so the welcome, this one will come up here, and we will create a list of ones, right? And that will happen automatically and transparently in MapReduce. When we say transparent in big data or distributed systems, it means that we don't know the details. It's a little bit counterintuitive, but that's what it means, right? And then the final thing that you need to do is to count how many ones you have, right? So that's what you do in the reduce phase. That could be expressed as a simple x plus y. So you're gonna go in pairs of ones, and just simply add them up. So that's what you do, and that's how it works, right? But this is slightly a little bit too quick explanation of what MapReduce is. Hopefully it is clear because you have some sort of experience, but hopefully when Mikkel explained this with the hands-on session, it will be even clearer. So MapReduce is just basically the programming paradigm, right? But the implementation of MapReduce, the first one that was actually publicly available and makes this MapReduce, let's say, it makes it public and makes it very famous, was the implementation called Hadoop. That is an open source framework written in Java. And this consists of multiple modules, but the two that are very important is this Hadoop distributed file system and the Hadoop MapReduce. So this Hadoop MapReduce module is implementing that idea of I define what the map function will do, I define what the reduce function will do, all that shuffle, which nodes are running what, that is decided automatically by this module, right? So that all of that happened transparently, is implementing that abstraction layer in there. This one in here is the one implementing that idea that I was discussing before about data locality, just keeping things locally in the different hard drive of your nodes in the HPC, all right? So that's why we mentioned this Hadoop, and Hadoop has been around for quite a few years now. But obviously, whenever we wanted to do some machine learning, we started finding some technical difficulties with Hadoop MapReduce. The main difficulty we found is, okay, it allows you to take into consideration that data locality, it allows you to do big data machine learning, but machine learning in many cases will have to go through the data multiple times and do many things. And when you try to use this implementation in Java of the MapReduce paradigm, you have problems because you're going to be serializing things many times in the drive and then read it again in the main memory of those local nodes. And in big data, efficiency will be key, right? So that's why many different platforms arise and they try to solve that problem. One of them that is really good, and that's the one we are discussing today, is Spark. And Spark is not re-implementing that distributed file system, it's only, let's say, liaising and managing that MapReduce, let's say, side of things. So it actually provides way more operations. Yes, MapReduce, it provides much more than that. And it provides a new thing that will help us understand how to do distributed computing in a, well, easier way, right? So there is no distributed file system. Actually, it will actually work together with Hadoop file system. And there are many different cluster management tools. I don't have the time to detail that, but just if you're not familiar with Spark, basically is data engine tool. And there are many different modules. And today we're going to be discussing quickly about the machine learning library. And Mikkel will be showing you something with the standard Apache Spark. So the first thing that they did, and the main, let's say, concept that I want to you to take out of this tutorial is the idea of a distributed memory abstraction. So they call it RDDs, resilient distributed data sets. If you think of a list in Python, for example, right? So imagine that that list is super big and it doesn't fit in the main memory of your laptop. An RDD could be considered the same thing, a list of objects, but that list is actually distributed across a number of computers, right? So that is the key thing that Apache Spark were able to provide. So you can do that from reading from Hadoop. And the most important thing, and why it's useful for machine learning, is this here, can be cached for future reuse. And I will get back to this when I explain the machine learning side of things of the tutorial. You can do many operations with one of these data structures that we just have in the main memory of multiple nodes. It's not only in the hard drive. Let's say that what Hadoop actually managed to do. Now we have it in different hard drives, but also in the main memory distributed across a number of nodes. And you can do multiple operations. And we will see three special operations: transformations, that are basically a modification and will create a new RDD here from an existing one. And they are lazy operations. If you are familiar with functional programming, you will know that a lazy operation means that nothing actually happens when you run it, but you will have to trigger an action to then actually return something to the driver. So we will distinguish between the driver, which is the computer. For example, when I'm running things in Spark in my laptop is here, but then the workers are going to be other nodes or other threads on my laptop working on that data as well, right? So things will get back to the driver whenever you trigger an action. Transformations will be happening in parallel. Persistence is all about catching things in main memory of those workers, of those computing nodes, to make sure that well, we reuse the information effectively. Spark is evolving really quickly. So we started with this RDDs. Now we talk about data sets and data frames, and we're going more into SQL type of programming, and you will see that during the tutorial. So if you're, thinking about, oh, what should I do? What language should I use if I want to use Spark? Good news is there are many different APIs available there. So you can use Scala, you can use Spark, you can use R, Python, and so forth. Spark is implemented natively in Scala. The one we're going to be using today is Python, because it has become really, really easy to develop any big data application now in Python. Because of the latest version of Spark, it has become really, really solid implementation, although they don't have everything that actually the Scala version of Spark will actually provide. So this is everything I wanted to discuss. I hope I'm not much over time. So I'm gonna unshare my screen and hand over to Mikkel. What is this? To stop sharing here. There you go, Mikkel. All yours.
Okay. No, I can't share it. Yeah. No.
Okay.
Okay. Thank you, Isaac. Welcome, everyone. Now I am going to speak about machine learning. How can we do machine learning in big data? After seeing what is big data and how we can deal with it, now it's the time for how can we do machine learning when we have big data. Okay, then Alberto will introduce some big data models in big data fuzzy models. Okay, so when we are going to address or to try to learn a model in big data, we can do it in two different ways. We can do it locally or we can do it globally. And these ideas are very simple. When we want to learn a model, we have to understand that we are working in a distributed environment. So we have many nodes and data is distributed across these nodes. So the easiest thing would be to learn local models. What this means is that we can learn a single model in its data chunk. So we can take the data from its node in the compute in the cluster, and we can learn a model, a decision tree, a neural network. It doesn't matter. We can learn a model like we do with scikit-learn, and then the thing that we have to do is to combine those models. So if we have data distributed, we learn a model for its data chunk, then we have an ensemble. So these local models are very easy to learn and are straightforward using common libraries like scikit-learn and integrating these libraries with Spark. Okay, but we will see that this also has some disadvantages. The other idea is to do it globally. So in the global models, the idea is to learn a single model with all the data as if in the same way as Google learned that model if the data would be in a single node. So this is much more difficult because we have to design the learning algorithm from scratch to deal with this distributed data. Okay, so in the case of the local models, we have some advantages, but also disadvantages. It is usually faster, much faster, because we are learning models with less data, and even the more partitions we have, that is, the more computing nodes we have with the same data, the faster we will be. Okay, so also the other good thing is that any existing model can be extended to a local learning approach, because we can instantiate it from scikit-learn on any other library and learn that model with for a single partition, and then the only thing we have to design is how to fuse the decisions from the different models in inference time. Okay, but this approach has also some disadvantages. Since we are going to learn many models as partitions we have, it will be slower in test time because we have many models to do the prediction. But the key problem is that we may have a loss of accuracy when we have many computing nodes or many partitions. For example, think of the most extreme case where we have a single example in each partition. If we try to learn a model for a single example, each model will learn almost nothing. So it will make no sense to combine those models. So when we are in a local approach, using some few partitions may produce an ensemble effect and improve the final results. But if we get too many partitions, then we will get an accuracy drop. The thing here is that the configuration of the cluster will affect the models we are learning. Okay, so in the global approach, we will try to learn a single model using the data as a whole. So we expect to get a greater accuracy, and the most important thing is that the accuracy won't change with different configurations of the cluster, and this is quite interesting. So it doesn't matter if we have 20 partitions or 200 partitions, it will just go faster, but the accuracy or the final model will not be affected. Okay, so also if we want to have an ensemble effect, we can also create a global ensemble. So it has also its advantages. However, the design of these learning algorithms, these global models, is much more complex than the local ones, because we have to design them from scratch for big data, for the big data scenario. So we will see that the algorithms in Spark MLib are designed in this way, in a global way, because if you want to learn locally, you can use any other machine learning library. Okay, so we have seen the different advantages and disadvantages of global and local models, and what is the best one depends on the application and what you need in that case. Okay, so when we are, this is like about the techniques, but now Isaac has spoken about Apache Spark. In Apache Spark, we have Apache Spark mlib library, and in mlib library, all the algorithms are designed in this global approach, as I have seen before. So in Spark mlib, we have different algorithms, machine learning algorithms from for classification, regression, clustering, and also collaborative filtering. We have methods for featurization, that is feature extraction, doing transformation, changing variables, creating new variables, and so on. And also one of the most interesting things that will be explained by Isaac in the hands-on tutorial are the pipelines, where we can combine different algorithms and featurization transformers to create a pipeline to avoid different problems that can appear when we are doing training and validation and testing pipelines. Yeah. Okay, so in Spark mlib, initially Spark mlib was designed with RDDs. RDDs are resilient distributed datasets, and they were the first structure designed in Spark for computing, for doing distributed computing with large amounts of data. And however, this was changed to a data frame-based machine learning library due to the advantages of data frames and data sets, where the speed, mainly the speed and the memory requirements are lower, higher speed and less memory requirements. As I have seen before, there are different methods for extracting statistics, doing transformation of features, and doing classification, regression, clustering, and so on. So this is almost everything about Spark mlib, and we will see more about this in the tutorial. Okay, so these are the different methods that are implemented. We have just to tell the most important thing here is that when we see that random forest is implemented in Apache in Spark mlib, or we have linear support vector machines, we have to understand that since they are designed specifically for big data, they are not exactly the same version as that we can find in scikit-learn, for example. So they are usually approximations for the original algorithms that are able to work in big data scenario. Okay, so that's it for machine learning in big data. Now Alberto will talk about how to create fuzzy models in big data.
Thank you very much, Mikel. Okay, here we go. Big data with fuzzy models. The idea of using fuzzy in big data, from a point of view, is mainly based on the uncertainty, the veracity that is inherent of the big data. You can recall the 4 V's of big data, and this is the veracity one. That is, we are acquiring so much information that we are unsure about how to represent it accurately. We have many heterogeneous sources. We have variety in data, incomplete data. So the whole veracity is in question. And in this context, we are in the fuzzy scenario, we are in the fuzzy EEE conference, and we acknowledge that fuzzy representation is able to deal somehow with all these issues. There are several problems in big data, and talk about uncertainty. This uncertainty can be addressed somehow by the membership degrees or extended fuzzy representation type 2 or any other. We have this vagueness on the data, and we can use the semantics of the linguistic labels to cope with that. And we have also 2 very interesting issues when we are implementing or designing local models. Is the lack of data in the partitions. If we are trying to scale out as Isaac told us, in a high level of scalability. And we know that using this fuzzy discretization, we are allowed the model to have a smoother coverage in the data partition. And for this data fragmentation, we also know that fuzzy models allow us to have a good generalization. But there is also a strong point to talk about rule-based systems and fuzzy rule-based systems. And this is a hot topic nowadays. We know that machine learning have very effective classification models, but these models do not allow to understand the inner procedure, the representation, internal representation, the inference, why the decisions are taken. So explainability, explainable artificial intelligence. There are special sessions and there were tutorials also on this topic that cover this topic. What? Why? Because it's so important nowadays because of the areas of study of the European regulation that we have different risks. And when machine learning and artificial intelligence is used for interaction with humans, it is needed to this right to explain. So rule-based systems fill this gap in data science with the comprehensibility. And we have this fuzziness of the membership function to have a software representation of the numerical variables. We have the semantics, which is the linguistic labels. So it's to ease the interaction between the expert, the user, and the decision support system. And we have also the learning stage, in which we translate the features into fuzzy variables, and we use the scripted smooth models that adapt well to this uncertainty. And for sure, in big data, there are plenty of different fuzzy based solutions. There are standard fuzzy rule-based classification systems. There are fuzzy associative classifiers. There is also evolutionary fuzzy classifiers, and there is fuzzy decision trees. And all of them have shown very nice and accurate results, comparable with some of the top base classifiers like decision trees. And a good compilation of all these solutions of fuzzy big data are covered in this paper, in this review paper that you have the title there. You can look for it. But in order for you to understand how do we implement a fuzzy solution for big data, let's take this naive toy example, this case study on the key fuzzy classifier. This key fuzzy classifier is the one and Mendel standard fuzzy system for regression adapted to classification. So rules are standard rules with all the antecedents and fuzzy labels. And finally, the consequent part with the class and the rule weight. And here, the most important issue is how to define the consequent. How to define the consequent. Because the antecedent are very simple. Each example derives an antecedent with the grid-based search. We just put the input space as a grid for the fuzzy labels. And in each square of the grid that as an example is covered, generates a fuzzy rule. So rules with the same antecedent can be created because there can be several points in the same cell, and if they have the same consequent, it is deleted directly. But if they have different consequent, the idea is to preserve the rule with the highest weight, the most confident rule. Okay. And we are going to design a big data solution for this procedure. And there are two different stages. First, to derive the model, to build the fuzzy model, and another big data procedure, MapReduce procedure, to make the classification, the testing stage. And depending on how we aggregate the consequence of the fuzzy rules, then we can find two versions with the maximum aggregation or with the average aggregation. And the idea is easy to understand, more or less. Let me explain it in detail. So let's start from the whole database. And the whole database is stored in this HDFS distributed file system. And from there, we can easily compute statistics to know the ranges of all the variables to build a global database. So the database is computed at the first stage using the whole information from the dataset. And we just build the standard ranges and we make the fuzzy partitions, homogeneous fuzzy partitions with triangular membership functions. And then we are going to apply a local learning procedure. So each split of the data that is stored in a different machine will be the one devoted to run the standard key modeling stage. So the learning of the rule base will be run in parallel for all the splits of the data. So a different rule base will be learned in different subsets of the data. But this is a problem because we will have same antecedents, same rules in different clusters, but we need a final rule base. So we need to make an aggregation. We need to summarize all these single or local rule bases into a single rule base. And how this is done? Well, the good point of fuzzy and linguistic fuzzy system is that the antecedents are directly comparable among each other, because it's very simple to collect every antecedent that is the same, can be collected, and a single function can merge all the rules that have the same antecedent. Okay, and we will proceed similarly to the original conflict resolution scheme of the classifier. In case of, so we have this picture here. We have different local rule bases. Each one it was constructed, built into a different machine, let's say, and we compile all the rules that have the same antecedent, exactly the same fuzzy labels, and we compare the consequent. We are going to aggregate the consequent that belongs to the same class label, and we aggregate them, the rule weight, using the average function. And this is a good approximation on the actual rule weight. In the end, it could happen that two rules have the same antecedent but different consequent, 2 or 3, depending on the number of class labels. And we proceed in the same way that in the standard key classifier. We kept exactly the one with the highest rule weight. And this is a design, a distributed design of the standard key algorithm using the guidelines of the MapReduce scheme. We first split, we map and divide the computation and run a single model local approximation on each cluster, in each machine of the cluster, and then we aggregate, we summarize into a single rule base, removing the conflicts that it could happen for rules that have the same antecedent and or different consequent. And this is an approximation of the standard FUZZIEEE key classifier, but for big data. If you need more information, you have the original reference in these slides. And it's time for us for explanation. Let's go for the hands-on tutorial. Let me stop sharing the screen. Oh, no.
Okay, thank you, Alberto. So now we are going to start with the hands-on tutorial. So the first thing we are going to see is the word count example that Isaac has explained before, but we are going to do it practically. So to do so, we are going to use Google Colab. I don't know if you are familiar with Google Colab. Isaac has shared the link that you can use in the chat. So please go to this link, and you can do the things at the same time that we are doing the hands-on, or you can try to focus on what we explain and then try to do it yourself. So, okay, I will share my Google Colab notebook now. Okay, this is the one. Okay, so for the ones that are not familiar with Google Colab is something that Google is providing freely. So it is like a virtual machine with some CPUs and GPUs to be used freely for 12 hours, and you can run it whenever you want from the web. So in this website, we can see a Jupyter Notebook. Jupyter Notebook is just a way of programming in Python where you can combine both text in Markdown format with cell codes. Okay. So here you can run, okay, some more zoom. Okay, Alberto is, okay, okay. Okay, here you can see that we have different cells with a play button. So you can run the cell with this play button, or you can do it like using Control plus Enter to run the cell. Okay, so the first thing we have to do here in Google Colab is to install a Spark. And we can do it. We can do that doing pip install PySpark with this exclamation. We are saying to Google Colab that we want to run this as in the command window, like in the terminal. Okay, instead of doing it in Python. Okay, this will install PySpark in Google Colab, so we will be using it after this step. So you can run it also in your notebook, or as I have said before, you can do it before after the tutorial. Okay, so this will download for this PySpark package, and we'll install it like in any Python installation. Okay, then the first thing we have to do is to start Spark. Obviously, here we are working in Google Colab, but Google Colab is not a computing cluster. It's just a virtual machine with some cores. So we will run the Spark in local mode. This just simply means that we are going to work with all the cores in our machine, but the same code that we are going to use here in the local mode should work in the distributed mode. Okay, so Spark has been installed, so we are going to start Spark creating a Spark session. So a Spark session is the entry point for Spark since Spark 2.0. Before Spark 2.0, the entry point was to create a Spark context, but for us here it's almost the same. We can get the Spark context from the Spark session. And here the things that we have to tell Spark is just where we are going to connect our Spark. So if you have a cluster, this should be an URL, but here is a local mode, and the asterisk indicates to use all the available CPUs. So here we create this Spark session in the play button with Control plus Enter. And after doing this, we can just start working with Spark. Okay, so the first thing we are going to do here is to import some libraries that we will need for this tutorial. And we are also going to download a text file that is will be used for our example. So if we execute this, we can check here in our here that Shakespeare.txt has been downloaded. These are the complete works of Shakespeare. So we will do the word count example with this file. Okay, we can check with the head command that we have downloaded, and this is okay. So after doing this, we can just we can start working with, in this case, RDBs. Okay, the tutorial has two parts. We have working with RDBs, and then we have working with data frames. Here we will have probably time only for doing the part with RDDs, but then you can follow that with data frames. For us, it's different in terms of speed, but the idea of map reduce and group by keys and so on is almost the same. Okay, so here what we want to do is just to count, to do the word count example in this Shakespeare.txt file. Okay, so this is the expected output for the 10 most repeated words. So we have the is repeated like 23,000 times. I is repeated almost 20,000 times, and so on. So we want to get this from this file. Okay. So to do so, I will copy this here. Okay. And the first thing is that Isaac has told you about transformations and actions in Spark. So if we just do this, like count these lines, I just want to show you that our file name is Shakespeare, okay? But if I put something else, this won't crash, okay? This will work, okay. There hasn't been any problem. Why? Because this is just a transformation. So this tells Spark, we are going to read this file, okay? If we don't do anything else, we won't get an error. To get an error, we need to do an action. And an action is, for example, a take. Take 10 gives us the first 10 elements of our RDD. And you have to think about the RDD as a list in Python that is distributed across nodes. So if we just do this, then we will get an error saying that the input path does not exist. Okay. So if I correct this, then yeah, then what we will get is the first 10 lines of the file, okay? Because this gives us the first 10 lines of the RDD, okay? So this is for reading the text file, we get the lines, and then we are going to start working with these lines using always this take just to execute what we are programming, okay? So the first thing that Isaac has told us was we have to get from each line, we have to divide the different words, okay? So we can do this. This bar is just to continue working in the next line, okay, to be more clearer, okay? So we can do a map thing. Before doing a map, I want to introduce you with Lambda functions. I don't know if everyone is familiar with Lambda functions. Lambda functions are anonymous functions in Python, which we tell Lambda X, for example, and we want to do X by X, okay? So if we program this, we can tell that this is a function, and then we can do F2, okay? So this will return 4. It's just how to name a function without doing def square and return X by X, okay? So these Lambda functions are very useful for our functional programming in map reviews. So we can do here something like take a line, okay, and divide it in different words. And we do this just with Python. We divide words with a split. This is take a string and divide it by spaces, okay? So we can now run this and we will get the thing that we can see here. Our RDD has been transformed to an RDD of lists of words, okay? But here we have a problem. We don't want these lists. We just want an RDD made of words. Okay, so for that, we have a special transformation in Spark that is called flat map, okay? And it's just the same as doing a map. What the map does is to apply this function, okay, to every line in the RDD, to every element in the RDD, okay? So the flat map does the same thing, but then does a flatten, like it removes these lists, okay? We will see the differences. These are the first 10 words in our RDD, okay? So after doing this, Isaac has told us we can take the word like as the key and then put a 1 to count the number of times its word appears. Okay, so to do that, we just simply we can do just another map function that takes a word, okay, and returns a tuple with the word and a 1. Okay, if we execute this, we will have this, the word with the 1. Yeah. Okay. After this is the most difficult part, maybe. We have to count this, and Isaac has told us about the shuffle phase and the reduce phase. Okay, so in Spark, both phases can be done. The shuffle phase is automatic, and then we program the reduce function, but it is not reduced, but reduced by key, the reduce from map reduce. Okay, so this will take another lambda function. Please, we use lambda functions because it is easier for us, but if you prefer to create that function with a name and then put here the name of the function, it is also okay. Yeah. So in the reduce by key method, what we are going to take are 2 values, and we will return a single value. So if you recall here the example from Isaac, we got something like big with 1 and 1 and 1 and 1, for example. Yeah. So this means that bigs appears 4 times. So this is after the shuffle where we are grouping all the tuples, yeah, with the same key, goes to the same place, and we create a list of values that we need to fuse. Okay, so this fusion is made with the reduce by key function, which takes 2 values, okay, and has to return a single value. So the way we reduce this to a single value is like using the reduce function from Python, which is only in integer tools. I will not do this, but the idea is that we are going to take a 1 and a 1. So the idea is we make 1 plus 1, this is 2, yeah, and then we will have 1 and 1. This is the idea, okay? So we take x and I and y, we sum these values, yeah, and the idea is after this, we will have this list with 2, 1, 1, then we will have a list with 3, 1, and then we can have a list with 4. Okay, but the thing is that if this is done in parallel, the idea can be different, and this can be something like 2, 2, and 4. Yeah, the result should be the same. So this function should be associative and commutative, and this is important because otherwise we can get different results depending on the order in what this is being executed, and we can't control that. Okay, so with this reduce by key, yeah, we can see the result. So yeah, sorry, this is a problem. I will remove this. Okay, yeah, I will have this here. Okay, so we have has been repeated 7,000 times almost. Yeah. So this is not the top 10 words, but just how many times it has been repeated its words. Yeah. So we can sort this, and to sort this, we can use this thing here, please. So there are different ways to do this. The most easiest one in this case is just to use take ordered instead of take. In take ordered, what we do is we want 10 elements, but these elements must be ordered with this lambda function. And in this lambda function, we have the word and the count. So these are tuples. So from these tuples, we should get we want to order this by the value. So we have to do word count, the first element. And since the default order is ascending, we have to do this like minus word count. Yeah. So if we do this, we will get the 10 most repeated words. And here we have a problem. If you see, this is the problem. we are getting that no word is being repeated a lot of times. So this is because after the split, some things like this appears. So we need to filter those. Just we can do this here. So we can filter this. Filter is like a map function, but just remove the elements that do not fulfill the lambda function. So we can take the word and we can remove those words that are, or we will retain only those words that are different from this. Okay, so just introducing this, yeah, we will remove this first, and you can check that this result is the expected output that we have here. Okay.
You have a question from Marcin there.
Yeah. Okay.
Feel free to unmute yourself, Marcin.
Thank you. I'm Marcin Mrukowicz from University of Rzeszów. I have one quick question. You use a Python here, and how about the speed? Because using Python will I mean that it needs convert from the JVM data frame or maybe JVM storage to Python to execute your code.
Yeah, this is a good question. We haven't time to speak about this. When working with RDDs, the performance in Python, yeah, it's worse than the performance in Java or Scala. Okay, so this changes when you move to data frames, because when working with data frames, everything is translated to the same code, to the same Java code, bytecodes. So because the things that we program are automatically compiled, so the performance with data frames is exactly the same in Java, Scala, Python, or R. Okay, so if you are working with Python, it is strongly recommended to work with data frames. Okay, so for this example, we are using RDDs just because it is usually simpler to understand. But if you want to do something serious, you can do it. You should use data frames or move to datasets. But datasets in Python doesn't make any sense because they are typed sets, and in Python it's like a different non-compiled language. So if you work with RDDs, the performance is going to be worse with Python. Is that your question?
Yes, it was. Okay. Thank you.
You're welcome. Okay, so this is the word count example. We are going to do some very slightly change to this in the next. So we are going to try to remove punctuation symbols, and for this we have this function already programmed. So I just want to show you here that if I copy the code, sorry, yeah. Okay, we can copy this code here. Okay, and we want to remove punctuation symbols. Okay, so this is a function, and we want to apply this function to a string. So the first thing we want to do even before the flat map is to apply this function to every string. So we can do this simply writing the function name here. Okay, so this is just telling Spark to execute this function for every line in our RDD. Okay, so we can see that it just works very simply. Okay, so here you have more examples, and just to understand the question from Marcin, I am going to show you very briefly the part with data frames. Just you have the solution. We will share with you the solution. Okay, I just want to. I will copy this because I have the solution. Okay, just to show you that there are many differences when working with data frames and when working with RDDs. When working with data frames, you can see things like select, alias, filter, group by, sort, and these are instructions typically used in SQL. Okay, so data frames come from a Spark SQL module. So the way of programming is very familiar for people that knows about database programming, but it's more unfamiliar for people oriented to programming, just programming. Okay, so here this is like this select explode is like the flat map. This filter is like the same filter we have seen before, and here it is much more easy to do the counting because we just group by word and count. We don't have to do that, put the one and then group by and then program the function. So this is like, if you want, you know what you want to do, it's easier to do it. And just simply repeat that this code here is translated to the same Java bytecodes, even if you are programming on Python, on Java, on Scala. So the performance is the same when we are working with data frames. And you can see that the result is also the same one. Yeah. So I think we don't have time for more with the word count example. Now Isaac will speak about the MLib example. Please, I will share now the link for the solutions, where you can see the solution for the different exercises, and you can try them in Google Colab very easily. If you have any questions, please ask without problems. Yeah. Okay, Isaac, so I will pass you the turn.
All right, thank you very much. I just posted the link to the one I'm going to be using, and due to the time, I was planning to, implement everything myself, but we're not going to have time to do so. So I just shared the one with my solutions, and we're going to just walk you through those. And I believe that would be way more useful than trying to rush it and trying to implement everything in 1 second. So hopefully you should be able to see my screen now. I'm going to make sure I have the chat here in case you have any questions. Some people are eating ice cream as well, which is good. It must be really hot down there in the south, but not here in the north. And so the aim of this tutorial and the aim of this is not really to give you a thorough, discussion about how to use the machine learning library in Apache Spark, because that would take us probably 10 to 20 hours to be able to get there, right? But just to give you enough to start off with this. So I'm going to reconnect here. So here is the solution to this. Once again, you need to install PySpark on this Google Colab. Otherwise, we're not going to be able to use it. And what I thought we could do is to work a little bit with a regression problem. And this regression problem is about energy data, as I'm working quite a lot recently on energy research, let's say, and prediction. So here is the data in my website. It's basically a machine learning data set that you need to download and to put it here in the Colab virtual machine. Otherwise, it will not work. So what is this about? So this is all about predicting appliances consumption. So what they did in this paper from Candanido, if I can pronounce it well, here is the whole paper, and what they did is they collected data for 4.5 months, and what they have is sensors measuring humidity and temperature inside a number of households, and then what they want to know is how much energy is used by appliances given these conditions. So they have in the kitchen, in the living room, and the laundry, and the office, and all this temperature and humidity, and they also have outside temperature and humidity, right? So when it's really hot, probably they are going to be using air conditioning, but that was in Belgium, so I doubt it very much. It's not like Alberto that at the moment is probably using his air conditioning to survive that heat wave down in Spain. So so this is the kind of data, and the idea is to be able to predict based on the input, based on the weather, being able to predict how much consumption will be done by those appliances. So we're going to be using Apache Spark. More specifically, we're going to be using the Apache Spark SQL SPI, right? So once again, I'm creating this Spark session, which is the entry point to Apache Spark SQL. So here is the information. And once again, I want to really say again, I'm not planning to go through all of it. I'm just planning to give you a few things that I believe whenever you walk on your own time through the document, you will, well, it will help you to make sense of it a little bit more easily, right? So the first thing I have to do is to read the data, right? So that's the data actually looks like this. So it's a CSV file that looks like this ugly here. So if I just basically from here, I was just printing the first 2 lines of this, and you get the header. In here, you got date, appliances, and then you see here the values. And something you will see already is that all the values are actually in between quotes, and that's going to be a little bit of a problem later on. So this is a CSV file separated by commas. So Spark has a beautiful function to deal with that kind of thing, and you can tell, hey, there is a header there, and therefore, can you please read it? So that's what we need to do. And you will also see that I'm catching that data frame. Why do I want to catch that data frame? Because I'm going to be reusing it all the time. So I don't want Spark to be reloading that from the hard drive. So that's going to be put in main memory, and then every operation that I'm going to be doing on it, it will be already in main memory of that virtual machine that I'm using. Something I didn't say here, when we use this here, what we are saying is, please do use as many cores as available. I'm not so sure about collab and how many threads we can have, but hopefully there is more than one. And so there is some sort of distributed computing in there. So if I check, for example, the type, so what you will get is a data frame from this PySpark SQL API. So here you have the description of the data. You will have time to look at that if you want in more detail. There are 2 funny random variables here that they put intentionally in the data set, and hopefully the model, the machine learning model, will actually be able to ignore that. So what they want to know is which ones of these features are actually important to understand the consumption of the appliances, right? So please, if you have any questions, please stop me at any point in time. Yeah, that's also very important. So we've got the data frame, and one thing we can do is to show that data frame, right? So I'm going to be running things, although some of them, the outputs are already there. So what you can see here is the first 5 rows of that data frame. When I do this, this is an action, and an action means something is going to be going back to the driver node. So as I said, we have a driver node, which is basically orchestrating everything that is happening, and the workers are doing something and are doing the job. When I say show 5, that will tell the workers, hey, give me the first 5, whatever they are, right? And they will go back to the driver, and then you print it. So it's very important you don't say show all of them, otherwise it will be a lot, because actually it's not a really big data set. There's 20,000 instances in there. So here you can see I read it, the date is in this funny format, and we will have to do something with it. Here is kilowatts hours or watts hour, consumption from lights, temperature, and so forth. So the first thing we will need to do with it is to pre-process that data set. First thing I want to do is to deal with this date in here. And for that, we can use something from the SQL PySpark API, which is called column operations. We need to, well, Spark has plenty of functions that are very highly optimized to be done on these data frames very, very efficiently. And many of those are like this one, which is day of the year. That's why we imported this F before, which is, if I show you again, is just the SQL functions that I name as F, right? So that's when I do F, it's just SQL functions. And there are functions for everything you can imagine. And so, for example, I wanted to get from this string here, I want to get just the day of the year that is. I want to get the hour. I want to get the month, right? So what I'm doing here is this function is being carried out directly on the column, right? And the column date, and doing this transformation from this to tell me what day of the year it is. And what I'm doing with this with column is a transformation on the data frame to add an additional column that will be called day of the year, and the values will be given by this function that is computing the day of the year. Something I wanted to highlight for this to be understood, because if I were to do this, that wouldn't have any effect whatsoever on the data frame. Why? Because data frames and RDDs in PySpark are immutable data structures, so you cannot modify that, right? So you need to assign that to a new variable df in here, right? So that's why we are doing all the time this. And if you're not familiar with this kind of style, but that's how it works. I don't have time to really go through all the details of this with column, but basically that has given me now, if I were to show you, and I always struggle to get this collab to do what I want, sorry about that. So if I now, well, just simply drop the date because I have created these 3 columns, and now I show you the different columns on that data frame, you will see that there are this day of the year, this hour, and month, and they are integer, but the rest of them actually are strings, because when I read it from a wrong format, and I want to correct that, right? So I know, because I read the paper in here, I know all of them are actually integers, right? So there are no categorical values, and I did my homework before coming to this tutorial. So I created a quick function that will be transforming that data frame and casting all of those to float, yeah? And that's what I'm doing here in this piece of code. So I'm not really explaining this step by step, but hopefully you will see that whenever I do that, and now if I print the schema, what you're gonna see is that all of them are float, are numerical values, which is what we need, right? So if we were to do machine learning with this, the first thing that we need to do typically is to split things into training and test, right? So this is, if you're familiar with the scikit-learn, it's gonna look very, very similar, but you need to remember that things are happening in parallel, right? So this random split, this seed here, yeah, well, we put it, I mean, I put it just because I'm used to do this kind of stuff, but that doesn't mean that you're gonna get all the time the same training and test. Why is that? This is a funny one. Depending on the, well, resources that you have available, whenever you create a data frame, it will be split into more partitions, into more, well, partitions basically. And the more partitions you have, this random split will work completely differently, right? So here we are doing it 70-30. It does the job. We have a train set and a test set, and now they're both data frames, right? So we've got that, and we could do many things. Here I just did some data visualization, just wanted to group by month, and just quickly see this, how much energy has been consumed in every single month. And I drew this histogram in here. This is taking quite a bit of time. This is actually running in parallel, right? So it's doing that kind of operation. I have the plot here. And one thing I see is from the data, knowing the month is quite useless, right? So we can just simply delete it by dropping that column from there. So is there any way, there is a question, is there any way we can fix it when we want starting 70% data training and next 30% as testing? I mean, the only way, if you really, really want to fix it and have the same one, is you do this and then you save that train and then you save that test. Otherwise, you're gonna, every time you do this, it might be slightly different. Well, every time you do it during the same session, it will work exactly the same thing. But if you change to a different computer, it will not be exactly the same. So my advice is you can save it as a new CSV file. And that would be if you need to repeat experiments. So yeah, thank you for that. A little bit of interaction is fantastic, really welcome. So I haven't even started with anything from the Spark machine learning library, but now we have the data, and you might believe this is now, okay, perfect. I just plug it in, I call a function that will have all these algorithms that Mikkel was saying that there are available already on Apache Spark. And here you try to just simply load that module linear regression, for example. I create a model, and then I try to fit that data frame. If I'm trying to do that, you're going to be highly disappointed. Why is that not going to work? Because expecting some sort of format. Yeah, and so the features are not the way that Apache Spark wants it. The way it wants it is, it wants a column with the output, and it wants another column with an array with all the features. That's the way it wants it. And we will have to do something to transform the data to get that in the right shape. And for that, basically, we'll have to use something called vector assembler, right? So this is the first thing we're going to do. But I'm going to get back to what the pipeline is, but just basically here you can see what we're doing, right? So basically, you're going to get, I'm going to run this. Well, this one is going to crash. So I'm going to create this vector assembler. What am I doing? So if I do, what did I do here? Oops. Live programming, they said. So what I'm trying to do here, if this wants to work now, yeah. So if I now check the content of this, so what I have here, have I run this well? Features. Okay, so now what I have in features code are all the features, all the columns, but the appliances, which is our target variable, right? So that's what we want to tell here. So we want to say all of them, you put them as an array, the output will be the other column. And this object, this will allow you to transform your original data frame into a new data frame with these two columns. And you could just simply use it doing something like this, transform the train, and then just use it with these two features, right? And you could just simply input that into the any model you want. However, anytime you want to do anything like that, you will have to transform the data and then load the model and create the model and so forth. What you can do is use the concept of pipeline. And I don't know if you guys are familiar with pipelines from the scikit-learn, but this is really similar. So what we're going to do is, rather than just transform the data and then do the next step, and then the next step, we're going to create a pipeline that will be transforming the original data into the shape that we want, then learning algorithm, then we will actually do a cross-validation, an internal cross-validation to determine the best parameters for that GVT that we're going to be using, gradient boosting trees, and then we're going to evaluate that pipeline, right? So here we've got the assembler ready. The second thing that you need to do is to get the model that we want to train, in this case a GVT for regression. I just basically load it from the package, something that you should get here quickly and in hand is the API, because that will be really useful. And basically you simply create it and you need to tell it, hey, I'm going to be using the appliances as the target output. That's the one I want to use. But we haven't done anything yet, right? The next step in this example is to explore different parameters for this cross-validation for this GVT regressor. For that, what you need to do, I'm not going to spend much time on this, is just basically create a cross-validator object with different parameters. So here we're going to explore the maximum depth and the maximum iterations for the GVT. So in total, we have 5 and 8 for maximum depth, and 10 and 20 for the maximum iteration. So that's a total of 4 different configurations we're going to try in the training set, yeah, when we build the model. To test those models, we need to create a way, we need to tell Spark how you're going to measure which one is the best, right? So we need a way to evaluate things, and that's what you do with this regression evaluator. In my example, I'm going to use the root mean square error as the metric. Here I say, well, the label is appliances and the one is prediction, right? That's the name, but we do it this way. It's just more, let's say, elegant. So here you create that object that is just telling Spark, hey, what I want you to do is to use the GVT that I created up here, right? So that GVT and this evaluator that I created here and these parameters, those are the ones you're going to be using to do anything. So far, I've been running this, and that was immediate response because nothing actually happened, right? I now can create a pipeline. What is a pipeline? So basically it's composed of a number of stages. In this case, only 2 stages. Assembler, which is transforming our original data frame with plenty of columns into 2 columns, and then the cross-validation stage, right? And that will give you the best model within the 4 models that you do here in training, and we'll train everything with the entire data, and that's the output of that. So we can now fit it. And now when we fit is an action, and that will take quite a bit of time. So it's going to take more than the time that we have for this tutorial. So I'm going to just keep it running, and hopefully I have the output there. You can just save the model if you want after that, right? So if you want to evaluate the results, how do you make predictions? You make predictions by transforming the test data frame, which is slightly funny, but basically what you do is use this pipeline model that we just trained. That's going to be going back to the driver, and you have all the trees in there, and that is used to transform the test and add an additional column with the predictions. So here you can see these predictions is a new data frame that will keep the original column and the predictions that have been made by this. So here you can see, yeah, it wasn't that good, was it? No, the appliances. So this is the real energy consumption, and this is the prediction, which is not too good. So if you look at the root mean square error, we're talking about 81 with this example, which is around 69 what we saw in the paper. So well, we are there. There is another question from whom?
We have a question, Isaac, from Ajay. Is there any way we can fix if we want to start in 70% of the data as training and next 30%?
I think I answered that question, I believe.
Okay.
Hopefully I did. Hopefully I did. Otherwise, tell me, Ajay, if you're not happy with it, please. If that was unclear. So yeah, I wait for your answer. In the meantime, I continue. So basically, just to wrap up quickly, so this is the way you can evaluate. So yes, here I added a few more things. If you want to go into the detail, you can actually try to get from that cross-validation we did internally in the training data, you can actually try to get which one was the best. And it's slightly tricky to get this, but I'm gonna leave it there for you. And here you see that the best one was with 23s in here, right? And you can then have a look at the importances of the different features based on that gradient boosting tree. Here, the output on the collab is not the best because it goes like, yeah, a little bit crazy. Something you will see easily is that the attribute 26 is missing. Why? It has 0 importance, and that's good because actually 26 was one of those random attributes that were created artificially. However, I believe 20, which one it is? 28 still has quite a bit. No, wait, 25 should have been ignored, and it's not. So it wasn't that perfect, right? So I think I did it a little bit too quickly, but hopefully you got a bit of a gist on how to work with data frames and the machine learning library. The key thing, I believe, and the key point here is the ability to create a pipeline in which what you can do is to put a number of pre-processing techniques all together, and then at the end of that pre-processing, at the end of that pipeline, you put your classifier, your regression algorithm, whatever you want to do, and then you train it, you fit the model, and whenever you have that, then you have your test data, raw data, and that will be shaped in the right way, and that will be used for making predictions with your model. And that's all I wanted to discuss to make sure that we were on time. So I'm going to hand over to Alberto, who is going to have a few more questions. I don't think there is a fuzzy means clustering directly in the Spark packages. Well, it might be in the Spark packages, but it's not definitely in the main API. Do you know, Alberto or Mikkel, do you know if this is somewhere in the Spark packages? So Spark packages
should be in Spark packages, because there are plenty of researchers that just share their source codes, and there are two. Well, at least there is the GitHub of the authors, but there is also one, let's say, single website which compiles everything. Is a repository of third-party implementations for Spark. Spark ML is very limited because these are optimized by the original authors of Spark, and they have the basics, but it works perfectly, scalability and so on. And there are several implementations that you can find in this Spark packages.org, in which there are different alternative implementation of clustering, this fuzzy implementation I mentioned earlier, and you can find it also in the GitHub of the original authors also, but are not, some of them can be not native to Spark, are not official releases, and they can work not at the perfect scale out issues. Okay?
Obviously, everything that is integrated within Apache Spark is highly efficient. Anything that is outside of Spark, it might not be the best one always, but it might be actually really good. Everything we do is fantastic, right? And it's outside of Spark anyways. So yeah, can you just finalize the presentation, Alberto? We've got only 5 minutes.
Okay, let's go because we are just finishing this tutorial, unfortunately. But well, we make time for the final match. I hope we keep you busy until then. And just what have we learned? I hope that you learned many things. I think that the Google Colab part of the session was very interesting, very attractive for you, because it was something different. It was something in which you can practice. Even you can write us afterwards of the ending of this tutorial to ask us for any doubt, any comment you have. You can use the Colab directly on your computer, and it won't be a problem. You won't rewrite our source code. But what have we learned? We learned that big data is kind of a new computational paradigm. It's not exactly high performance computing. It's just something else. It's parallelization, transparency, fault tolerance. It is very dependent on cloud computing. You need to use an Amazon Web Service. You need to use your own cluster. You need to use Azure, Google Cloud Platform. You need to use anything to be able to upload your files there, to distribute it along different hard drives, and then apply the parallel scalable machine learning solutions. You have the Spark framework, is the de facto standard. All the solutions, the main solutions are in there. You can use Python, you can use R, you can use Java, you can use the language that you are more comfortable with. But in the case of machine learning, we suggest the use of data frames and the SQL like for managing this data. So what do you need? You need access to HDFS for the parallelization in your own cluster of servers or at cloud computing resources. We recommend Scala because it's native to Spark or even Python, and all the MLlib, Spark MLlib library. It's very similar. The functioning, the writing style is very similar to scikit-learn. All these pipelines, all these data frames, everything, this fit and predict is very scikit-learn-like coding. Okay, but you need to be up to date because there are plenty of new solutions arising in the literature. You can use notebooks for those of you that are not experts. You can use our notebooks, different notebooks that other researchers make available. Implementing your own solutions is not straightforward because you need to think about all this divide and conquer style of doing things. Is not sequential anymore. And also you need to think about the data that you can get in public repositories, APIs, that are usually not the best. They have some redundancies, some problems, and you need to think about transforming this big data into a small data to dig into the information, to apply data preprocessing, because in general, big data has, as I said, has so much information that in the end, especially in tabular data, where the information lies, is a very limited subset of the data, and data preprocessing is vital in this context. We are moving towards this data-lake concept. We need to think about this small data because there are few case studies in the public repositories. As I said, there are not so much preprocessing techniques, but in here, fuzzy models can do something because of this data quality that we need to address. We may think about smart feature selection, we must think about fuzzy ensemble for vertically partition. We can think about fuzzy decision trees also, good implementations available there. And of course, big data need explanation, interpretation, visualization, and in there, fuzzy modeling has the power, the good point is in there. So soft computing approaches and fuzzy approaches, for me, is very significant to be applied in big data. Has not been widespread because a standard solution, so people, data scientists, use the libraries they have at hand, and we need to put an effort to make more and more implementation. In the end, I will provide you some interesting references, bibliographical references with the latest implementations on fuzzy logic in machine learning for classification, regression, association, because they have many advantages. They have the management of imprecise and uncertain information. They have good behavior in the event of lack of data for these local models. They behave well even for local models. And for sure, they allow the comprehensibility for explainable artificial intelligence. And we need to think about also a bet for evolutionary fuzzy systems, because they boost the abilities of the modeling in fuzzy-based models. There is a bottleneck of the fitness computation, but we need to think about how to redesign this part to make this scalability at hand. And we have some code of our approaches in here, but as I said, there is this Spark package software repository that you can also visit. And just to finish, there are the latest, to the best of our knowledge, that we compiled in here some good references, useful references for those that want to use fuzzy modeling in supervised machine learning. We have these recent references that you can take a look to them and ask us, because we are co-authors of some of these papers. You can ask us if you want to start doing your own line of research in fuzzy big data. That's all. We are on time. So if you can pose some questions, we will be happy to solve anything you have in mind. Thank you very much for your attention, for being here on a Sunday. Okay, Corrado has a question.
Yes, my question was about how much control do we have in distributing data in the different computational units? I mean, in the first part of your tutorial, you mentioned the key method for generating fuzzy rules. And I suppose that if data are distributed in a different ways in the computational nodes, you may end up with different fuzzy rules, or at least fuzzy rules with different weights. So is it possible to control the way data are distributed among the computational nodes? Is there a possibility to imagine a method, a preprocessing, let's call it this way, preprocessing method to optimally distribute data among the computational nodes?
This is transparent for the distribution file system. Distributed file system, you just upload, so you have like the standard file system, and then you upload your data in this distributed file system, and then it automatically splits into different hard drives. And then you have a parameter for running the big data script, in which you just tell how much partitions do you want. So the original file is split into, let's say, 1,000 files, and then you say, okay, but I want chunks of 100 files. I have 100 partitions, 100 functions in parallel. You can control that, but what you not control is how much lines or how much data is or in each of these files. And this sometimes is, you get very, very confused about, you run it twice, you get different results because data is shuffled And this is quite one of the hard parts of big data. I don't know if Mikel and Isaac can extend this answer.
Yeah, what Alberto has said is true. You can, ideally, this is transparent for the user, so data is distributed and you don't know how this is distributed, and it's not easy to control that distribution. So anyway, you could do something like you have said, some pre-processing in which you use key values to send all the data you want to a specific node or a specific partition. But anyway, it is not easy to ensure which data goes to what place. So that is a problem here when you want to do things like the one you mentioned. Yeah.
This makes me think that it is important to define methods that are agnostic with respect to possible distribution of data among computational nodes. This is
solution.
The idea is if you work with global methods, you don't have this problem because it doesn't matter where the data is. This problem is when you are using local models which work with chunks of data.
Yeah.
That is much complicated to design and develop. It's very much complicated.
Okay, thank you. Thank you very much.
Thanks to you. Marcin has another question, please.
Yes, thank you. I have some background with Spark, and I have one problem. Usually, if you want to use Python libraries and Python environment, it's quite difficult to use it with Spark because Spark usually is good when you use only Spark, not when you want to use some Python like NumPy or other libraries. And is there any way to use Python libraries with Spark efficiently?
Why not? Why is it the problem? I don't understand why you think.
I suppose that the user-defined functions and all that stuff is a bottleneck in the version 2 of Spark, but it's supposed to be fixed in this new version 3. I don't know if this is the issue that Marcin is experiencing.
Maybe it's if you are working in a computing cluster, you have to ensure that the libraries, the version of the libraries that you have in each node are always the same, and you have the same environment in all the computing nodes, because maybe you want to import NumPy and you have NumPy installed in your driver, but it is not installed in your worker. So and they can be different versions, so they don't understand what you are writing in one and the other. So I don't know if your problem is for this, but you have to ensure that all the versions are the same in all the nodes. When you are working in local mode, you usually don't have this problem because you are working with the same installation. Maybe it's about this.
Does it answer your question?
I have another problem. It's rather the way that UDFs are not as good as Spark native implementations, and the official documentation said that you cannot use UDFs for really big data. So it's a problem. So you cannot use Python libraries endlessly. There is a problem that there is a biggest data that you can compute with Python, and Spark could Spark cluster could compute it, but not in Python.
Yeah, it is a bit of a problem, as Alberto was saying. UDFs in Python, I mean, I believe now from version 3 are working a little bit better, but it's still not ideal. And actually, I wouldn't advise using UDFs unless it's strictly necessary. So I would say if you are going into UDF type of thing, it's because you're designing really big data models. And in that case, I would advise to go to Scala. Because that's what you're doing. If you really want high performance and you're developing your methods, you really need Scala or something like that. But if you want just to use whatever is available, Python is fantastic for that.
Thank you very much for your answers.
Thank you for